Hello everyone, today we will work on exercise set 15.4. That's a polar coordinate and polar integration. I think that's the title. That's a polar integration. Now to remind us the polar transformation, suppose I have a coordinate x comma y in rectangular coordinate system. Then that coordinate may be represented in polar by using r theta, where the r is the distance from origin to that point, and theta is the angle in standard position. Well, angle in standard position means it's counterclockwise from positive x-axis. Now, for that reason, then we see that r is equal to the square root of x squared plus y squared, right, by Pythagorean theorem. And theta is equivalent, not necessarily equal to, tangent inverse of y over x. Okay, now from here we also see that x is equal to r cosine theta, y equals to r sine theta. Now, as for the integration in polar, suppose I have a curve. So let's say I have a curve and call this r theta, the function r as a function of theta. Then the area, I think, you know what? Instead of using a function, let's use the rectangle. What we call rectangle in polar is something looks like this rectangle here, okay, which is actually consists of, the area is approximated by the change of the radius dr and the length here. Maybe I use different color, this one, the length here. Now the length of that arc there is r d theta. So where r is the distance from origin to that arc, and the theta is the change of the angle there. Okay, so the rectangle that we have in rectangular coordinate system for the dx dy, now represented by this rectangle, which is r d theta times dr. Okay, now that becomes the foundation of our integration later on. So our double integral over domain D of f x y dA, when we convert that to polar, that becomes double integral over domain D of f r theta. Okay, but the dA becomes r dr d theta. Okay, so this guy here now becomes this. Okay, now I noticed that when I look at my lectures, I have done some problems at the beginning of that exercise set. So let me do more, but it seems like I cannot avoid doing some odd problems. Let's say I do number 7, and I hope by doing some earlier questions you guys get some feeling on how to convert the rectangular integral in rectangular coordinate system into polar. Okay, so number 7, we have double integral over domain D of x squared y dA, where the D is the top half of the disk with center origin with radius 5. The top half of the disk. Oh, Thomas, hold on. It says this, why it doesn't say circle? A circle, or a half circle, or a semicircle just refers to only the boundary of that circle. Okay, now a disk refers to not only that circle but also inside of that. Okay, so when we say half of the disk, means is the not only the perimeter or circumference of the circle, but everything inside that circle, the plate. Okay, now so it's the top half of the disk with center origin with radius 5. Okay, so that's the domain D. So we can see here that the radius is from 0 to 5, and the angle theta is from 0 to pi. Okay, now then we do the transformation here, integral r d theta. The theta is from 0 to pi. R will be from 0 to 5, and x squared becomes r squared cosine squared theta, while y becomes, let me move this a bit, and y becomes r sine theta. Now I want you to notice the substitution. The x squared becomes this, the y becomes this, and then the dA becomes this. It's too close to each other, huh? Let me redo it then. Let me redo it. I tried to save some space, but if it compromised the view, then let me just redo it. So the x squared becomes r squared cosine squared theta. That's my x squared, times y, that's r sine theta. That's my y. And my dA now becomes r dr d theta. Now simplifying them give us integral from 0 to pi, integral from 0 to 5, r to the 4th cosine squared theta sine theta dr d theta. Okay, and because the integrand are separable, the r and the one with theta terms, theta factors, right? Okay, and the domain is a rectangle, all constant, then I can use Fubini theorem if I want to. You can also do just integrate it from inside out if you want. Let's just do it inside out. But if you want to use Fubini's theorem, it's totally fine. Then you will get 1/5 integral from 0 to pi of cosine squared theta sine theta r to the 5th from 0 to 5 d theta. That gives us r to the 5th, right? R to the 5th, but this is 5. So there will be 5 to the 5th over 5 integral 0 to pi cosine squared theta sine theta d theta. Okay, which give us 5 to the 4th, right? And then the inside, if we do substitution, u equals to cosine theta, then du will be negative sine theta, d theta. And substitution, this is 1, this is negative 1, u squared, negative du. Oh, that's an even function, huh? Well, just do it like usual. 5 to the 4th times 1/3, actually negative 1/3 u cubed from 1 to -1. That's 625 over 3 times 2. So 1250 over 3. Okay, that's for number 7. I think it's not about the last couple of steps though. I think it's more about the first couple of steps. That's the one that you need to pay attention. Okay, how to do the substitution. Okay, and from there we basically deal with that the way we dealt with x and y. Okay. My very big advice is like be very patient when you do the substitution. Okay, because if you miss anything, there's a chance that the integral becomes so not doable. Okay, yeah, so be careful when you do the substitution. Number 9. Number 9, we have double integral over domain R of sine x squared plus y squared dA, where R is the region in the first quadrant. Okay, first quadrant, between circles with centered origin with radius 1 and radius 3. So this is the domain of R. Okay, that's the R. So far so good. Now then we go back to that substitution. Okay, well, x squared plus y squared equals to r squared, right? So this becomes double integral. The theta will be, oh yeah, the radius will be from 1 to 3, and then the theta will be from 0 to pi over 2, 90 degrees, right? Okay, so the outer integral, we use the angle, and the inner integral is 1 to 3. Okay, of sine r squared, then times r dr d theta. Again, take a look on the substitution. This guy becomes r squared, and the dA becomes r dr d theta. Okay, and notice that at this point we really need that extra r because of the substitution we need. Okay, so u equals to r squared, du equals to 2r dr, and the limit of integration for r, u1 is 1, u3 is r squared is 9, right? So this guy later on will become 9. Okay, so this is integral from 0 to pi over 2, integral from 1 to 9 of sine u. Now r dr, this is r dr, is du over 2 d theta. Okay, now integrating it, integral of sine is negative cosine, so I pull the 1/2 out. That's negative cosine u from 9 to 1 of d theta. Oh, actually it's a rectangle and the integrand is independent of theta, so that will be just the length of the interval. Okay, so this is 1/2 times pi over 2 times cosine 1 minus cosine 9. Okay, that will be pi over 4 cosine 1 minus cosine 9. I honestly don't like this though. I honestly don't like this. We don't know what is cosine 9, that's the thing, right? But well, this is the exact solution. Okay, that's for number 9. Let's see, let's try number 12. Let's try number 12. And again, you will see how important it is to do the substitution correctly, because otherwise, if in my number 9 I don't have that r, that integration is nearly impossible to do. Okay, or maybe even impossible to do. Okay, number 12, double integral over domain D of cosine square root of x squared y squared. Let me copy that down first. Number 12, double integral over domain D of what's that? Cosine of square root of x squared plus y squared dA, where the D is the disk with center origin with radius 2. Oh, so that's a disk with center origin with radius 2. So the whole thing, huh? Okay. So the r will be from 0 to 2, and the theta will be from 0 to 2 pi. When we do the substitution, the theta will be 0 to 2 pi, the radius will be 0 to 2, cosine of square root of x squared y squared. Well, x squared plus y squared equals to r squared, so doing the square root will give us the r, right? Times dA will be r dr d theta. Okay, now notice that the integrand is independent of theta. In fact, the inner integral also independent of theta. So this becomes, if we use Fubini's theorem, this becomes integral from 0 to 2 pi of d theta times integral from 0 to 2 of r cosine r dr. Now, the first integral will give us the length of interval 2 pi. Okay, now the second integral, however, we need to do integration by parts. Okay, I hope you remember how to do the integration by parts. But I think I will do it by tabular method. This is 1, this is 0. Integral of cosine is sine. Integral of sine is negative cosine. So that will be 2 pi times, parenthesis, r sine r plus cosine r. That's the tabular method. Okay, from 0 to 2. Okay, so when r equals to 2, we get 2 sine 2 plus cosine 2 minus 0 plus 1 when r equals to 0, right? Then we get 2 pi times 2 sine 2 plus cosine 2 minus 1. That's for number 12. Oops. Okay, now so far we just learned to substitute the integrals. We substitute the variable xy into r theta, look at the domain to catch the limits of integrations. We replace the dA becomes r dr d theta. That's what we have done so far. Now, in the next couple of questions, we will learn more on how to put them into, what if we already have a polar curve, the curve in polar equations, and then we want to find, in this case, like number 16, if we want to find the area of a region. Okay, let's see. use a double integral to find the area of the region enclosed by both cardioids. R equals to 1 plus cosine theta. Now this one, I hope you can memorize. Okay, 1 plus cosine theta, so that's 2, this is 1, that's 0. So this, it looks like this. That's the cardioid. Okay, and then, so this is the first one. And then the second one, 1 minus cosine, R equals to 1 minus cosine theta, will be this part here. It looks the same, but you reflect that with respect to y-axis. Okay, so we are looking at the one inside of both, must be this one. The one here. Okay, now, but then by symmetry, we need to find the area, right? Okay, so by symmetry, the area of the green or of the yellow region, the one that looks like an 8 there, right, is equal to the area of that part in the first quadrant, in quadrant 1. Can I do that? In other words, instead of doing 4 integrations, I will just do one of them. Okay, and that one integration that I do will be this one. Okay, will be that one. Okay, so the area that we need is equal to 4 times double integral of the curve in red. The curve in red is 1 minus cosine theta. The curve in red. You know what? That's not the z. That's from 0 to 1 minus cosine theta. Okay, that's the radius, right? Let me enlarge that a little bit. So what we see there is this. As the theta moves, let's say this is the theta. Okay, the error actually starts from 0 and gets out at that point, which is r equals to 1 minus cosine theta. Okay, now then the theta itself will move from 0 to pi over 2. And then r d theta. Okay, which is equal to 4 times integral from 0 to pi over 2 of 1/2 r squared from 0 to 1 minus cosine theta d theta. Now, I hope you remember something from calculus 2. In calc 2, the formula, let me remind you, in calculus 2, the area in polar is given by single integral, 1/2 of r squared d theta, where the theta is from alpha to beta. That's what we have in calc 2. Now notice what happened here. When we set it up in double integral, the next step actually looks like what we have in calc 2. Okay, the 1/2 r squared. Right? Okay, now then from there I go, let me multiply the 4 by 1/2, the 4 by 1/2, then give me 2. Okay, integral from 0 to pi over 2 of 1 minus cosine theta squared d theta. Okay, now how to integrate it from there, that's another story. But that's basically calculus 2, right? What we learned in calc 2. This is 2 times integral from 0 to pi over 2, 1 minus 2 cosine theta plus cosine squared theta d theta. Okay, and this is 2 times integral from 0 to pi over 2 of 1 minus 2 cosine theta plus 1 plus cosine 2 theta over 2. Double angle formula. Okay, or power reduction formula to be more precise. Okay, because we cannot integrate cosine square. You know, we need to make it into multiple angles and then integrate it from there. Okay. I think at this point it's useful for us to utilize some trick that I think I already taught this in my Calc 2 class, but it will be nice to remind ourselves. Okay, when we integrate a constant, that's basically a constant multiple of the length of the interval. So when I integrate this guy here against 0 to pi over 2, I will get pi over 2. Okay, then minus 2 times, now what is the integral of cosine theta in the first quadrant? I expect you guys to memorize this though. Integral from 0 to pi over 2 of cosine theta d theta, that's equals to 1. Okay, basically I'm saying is the area under the curve from 0 to pi over 2 for cosine theta, or from 0 to pi over 2 of sine theta, the area equals to 1. Okay, that will speed up your computation. Instead of integrate the cosine or integrate the sine, you already know the value, you know. Okay, so that becomes 2 times 1 plus, this is 1/2 times the length of the interval. Okay, and plus, so let me do this guy here will give me this. And the last part will give us 0. Is it right, 0? Yeah, it will give us 0. Use different color. This guy will give us 0. Why, Thomas? Why is it integral of cosine 2 theta from 0 to pi over 2 becomes 0? The explanation is from the graph. Of course, then it depends on how strong you are in your trigonometry about the graph of trig functions. But if you think about that, integral from 0 to pi over 2 of cosine 2 theta d theta, we interpret that as the area under the curve for cosine 2 theta from 0 to pi over 2. Okay, that's for cosine 2 theta. Y equals to cosine 2 theta. Now, the area under the curve cancels out. Okay, they cancel out. Now, of course, if you want to write more and think less, you can just integrate that. You will get 1/2 sine 2 theta from 0 to pi over 2. That's 1/2. Sine pi is 0 minus sine 0 is 0. That's 0, right? Okay, but if you imagine the graph, cosine 2 theta have frequency twice faster. The what's that? The period is only pi, right? The period is pi. So it will finish one cycle in pi, and up to pi over 2, it's already have the top part and the bottom part cancel each other. Okay, now with that kind of, I basically teach you sideways here, but if you know this fact, you can do this computation a lot faster. Okay, so this is 2 times pi over 2 plus pi over 4, that's 3 pi over 4 minus 2. Okay, which is equal to 3 pi over 2 minus 4. Okay, now you see that I can be efficient in my computation if I know some little fact. Otherwise, then you need to write a lot more. What is the integral of cosine, right? And what is the integral of cosine to theta? And then you plug in 0, you plug in pi over 2. It's too much, unnecessary work. Okay, now another issue with this question is your ability to graph this. Now you may say, Thomas, can I use my graphing calculator? Actually, I don't allow you to use graphing calculator, but if you use your TI-83 or TI-84, go for it, you know. But it's like something you're supposed to know already, you know. Okay, like the one they asked us in this course, actually the one quite reasonable. Okay, now let me go on with number 18. So I have to say that it really depends on how well you were prepared in your trigonometry class and also in your calculus 2 class. You know, I can review a little bit about the polar graphs, okay, but it's definitely not in the sense that I spend the whole like a big portion of the class for those. Okay, in other words, make your calculus 2 instructor be responsible. Okay, yeah, that they're supposed to do their part and insist that on you way before this. Okay, let's see number 18. And I'm not saying that you cannot do it, you cannot learn it right now, but it's something you're supposed to have learned from Calc 2. Okay, in Calc 3 you try to review that yourself. Okay, number 18, find the area inside the cardioid again and outside the circle r equals to cosine theta. Let me try to remember the questions. So we have two there. First one is the cardioid 1 plus cosine theta. That's the one looks like this. You can kind of plot it, like if you want to feel it, right? Okay, you can plot it, well, when theta equals to 0, that's 2. When theta equals to pi over 2, cosine theta is 0, so 1 plus 0 is 1. When theta is pi, that's negative 1, the radius becomes 0, and so on. So this is 1 plus cosine theta. Okay, now the second one is r equals to 3 cosine theta. 3 cosine theta means it's a circle centered at 1.5 with radius 1.5. So we are talking about this region here. Okay, now we have issue that seems like from when you shoot from origin to here, you will get the cardioid part, but when you shoot after a certain angle, when you shoot there, you will hit the circle part. So there must be some point where they intersect, and we need to find that intersection. We need to find what is the theta here that the boundary change from the cardioid, call this alpha then, the boundary change from cardioid to circle. Okay, now at that point the r equals to find the angle alpha where the first curve intersect the second curve. Okay, let's call this C1 and this is C2. Okay, we set the radius equal to each other. 1 plus cosine theta equals to 3 cosine theta. So 1 equals to 2 cosine theta. So cosine theta equals to 1/2. So the theta in quadrant 1 must be pi over 3. Right? And in quadrant 4 also you can see here that's negative pi over 3. Okay, we just do the one in the first quadrant. What is the reason? Because the region above the x-axis there is symmetric with the region below x-axis. So the area we will do later on will be double the one in the first quadrant. Okay, the area equals to 2 times area in the first quadrant. Let me play with the color. Okay, and that area in the first quadrant will be broken into 2 parts. The first double integral plus the second double integral. The first double integral is the one under the cardioid. This is the first part. Okay, and then the second part is the one under the circle. Okay, now the first part, the angle is from 0 to pi over 3. The radius is from 0 to 1 plus cosine theta, r dr d theta. The second part is from pi over 3 to pi over 2 of the circle from 0 to 3 cosine theta, r dr d theta. Okay, I want to play with the color again. So let's say this one here, this is the first part. This is the first part. And this is the second part. Okay. Now let's see, do I need to compute it or just set it up to find? Okay, well, we need to find it and I need to work it out then, which is not really a big deal. Still do it. Okay, so this will be equal to, let me pull it here, that's 2 times integral from 0 to pi over 3 of 1/2 1 plus cosine theta squared d theta plus integral from pi over 3 to pi over 2 of 1/2 3 cosine theta squared d theta. Okay, that equals to, well, I will just distribute the 2 to kill the 1/2. Okay, so the first integral, well, it becomes integral from 0 to pi over 3 of 1 plus 2 cosine theta plus cosine squared theta d theta plus 9 integral from pi over 3 to pi over 2 of 9 cosine squared theta d theta. When I integrate, let me integrate them instead. So I will get theta plus 2 sine theta plus integral from 0 to pi over 3, 1 plus cosine 2 theta over 2 d theta. Okay, that's the first one. And then the second one will be 9 over 2 integral from pi over 3 to pi over 2 of 1 plus cosine 2 theta d theta. I'm actually missing something. Let me do this from 0 to pi over 3. Okay, so the first term becomes pi over 3. The second term becomes 2 times, what is sine pi over 3? Sine pi over 3 is radical 3 over 2 plus the integral from 0 to pi over 3 of 1/2, that's a constant, so that's pi over 3 times 1/2. Okay, plus 1/2 times cosine 2 pi over 3, let me just write it down, minus cosine 0 plus 9 over 2. The length of the interval there is pi over 2 minus pi over 3 plus sine 2 theta over 2 from pi over 3 to pi over 2. Now, if you're confused, then trust me, the reason is because some of them I plug in numbers, some of them I still integrating, you see? Okay, so in practice, it is actually better to just integrate them first and then plug in numbers at the same time. Okay, yeah. But if you can handle the possible confusion, then you do it the way I do. Okay, so let me go on. This is pi over 3 plus radical 3 plus pi over 6 plus 1/2. What is cosine 2 pi over 3? That's negative radical 3 over 2 minus 1 plus 9 over 2 times pi over 6 plus 1/2 sine pi is 0 minus sine 2 pi over 3 is, hold on, cos, that's actually radical 3 over 2. I'm sorry, this is actually negative 1/2. That's cosine. I missed that bit. Sine. Oh, painful, huh? Bear with me. It's algebra all the way. And this will be minus, that's 3/2. That's negative 3/4. Plus, what is this? Cancel this with this 3, and then this 3, 2, just that 3/4 pi, 3/4 pi, and then negative 9 radical 3 over 8. I hope I don't make miscomputation. Yeah, anything after this is a combining like terms thing. Okay, let's see this one. This guy plus this guy plus this guy. LCD 12. So there'll be 4 plus 2, 6 plus 9, 15. So there will be 15 pi over 12, and then minus 3/4 minus radical 3 over 8. The number's too ugly. Let me go back and check. I think if I have my issue with the substitution, let me do it one by one. From here to here, the length of the interval. Okay, that one is good. From here to here, that's 2 times sine pi over 3. Sine pi over 3 is radical 3 of 2. Okay, that's good. Sine 0 is 0. Okay, and then for this one here, 1/2 times the length of the interval. I'm good. And then the one here is 1/2. Oh, that's where I make a mistake. If I integrate that, it's supposed to become sine, not cosine. Okay, so this should be sine. Okay, so sine 2 pi over 3 is radical 3 over 2 minus 0. So this guy becomes radical 3 over 4. Am I right? And then let's see this one, integral of 1. I'm good. So 9 over 2 times pi over 6, cancel this by 3. So 3 4 pi, okay. And then integral of cosine 2 theta is sine 2 theta over 2. That's the 1/2 2 pi over sine 2 pi over 3 is that. Okay, now then I need to recompute this. I think my pi is okay. No, I don't have this thing. So radical 3 minus radical 3 over 4 minus 9 radical 3 over 8 times 2 becomes 8 times 8 over 8. So 8 minus 2 is 6, minus 3 minus 9 is negative 3, radical 3 over 8. Reduced by 3, that will be 5 pi over 4 minus 3 over 8. Yeah, that's the answer. Okay, now you see that if I don't organize my work, I will have a very hard time to check my work, right? Now let's look back to this question. What makes this question, I think this question is long, okay, but the focus for now should be on how to set it up. Okay, the curves, this is the curve, right? Maybe I use another color, another highlight. This is the set of two curves that we are dealing with. Okay, when we graph them, notice that it's symmetric with respect to x-axis. Okay, it's symmetric with respect to x-axis. I want to hold back that statement. Am I? Yeah, it's symmetric with respect to x-axis, and therefore we have the double part here, right? Okay, such that then we deal with only the region in the first quadrant. Now in that first quadrant, when we zoom it in, when we see that further, that first quadrant actually have this kind of configuration in which at certain angle, the radius actually goes from that ended at the cardoid. After that angle, it ends at the circle. Okay, and that angle is pi over 3. Angle pi over 3. That's why then we need to break it up from 0 to pi over 3. The radius is 1 plus cosine theta, the cardoid. From pi over 3 to pi over 2, the radius is 3 cosine theta. Okay, and then from there we go further. Okay, don't forget, the important part is really the setup. Okay, you need to set it up right. If you don't set it up right, anything you do after that is really terrible. Even if you set it up right, like the way I did here, the result is terrible. Right? It's kind of tedious, I admit. But imagine if I don't set it up right, that anything I do there will be a waste of time. Okay, now that's for number 18. Let's move on. I try my best to do as many examples as possible. Okay, number 20. Use polar coordinates to find the volume of the given solid. Below the paraboloid, this is the paraboloid, and then above xy plane. What is the paraboloid look like? Z number 20. Z equals to 18 minus 2x squared minus 2y squared. That's 18 minus 2 times x squared plus y squared. If I change it into cylindrical coordinate, that's 18 minus 2r squared. If this is r, this is c, the vertex is 18. The radius is 3 then, the r is 3. This is 3. And then we rotate, revolve that with respect to z-axis. So that's what the graph look like. Okay, now above xy plane means the c has to be greater or equals to 0. Right? Okay, that implies you will see the r will be from 0 to 3, while the theta is from 0 to 2 pi. Imagine if you see this region, here from above. If you see that region from above, you will see a disk with radius 3. And that defines our domain now. Okay, so the volume will be double integral over that domain D of z, which is 18 minus 2x squared minus 2y squared dA. That's the integral. Now, because of the shape of the domain, it's a disk, and the nicety, how to say that, the integrand will be a lot nicer if we treat that in polar, right? So it takes two things. Okay, it takes two things. It takes two things. First one, the domain. The domain is a nice shape if we see that from polar point of view. And the other thing is like the integrand is nicer when we convert it into polar. Now using those two, we have better reason to convert this into polar integration. Integral from 0 to 2 pi, integral from 0 to 3 of 18 minus 2r squared r dr d theta. Okay, now notice that the domain of the integral is a rectangle, right? And the integrand, in fact, is independent of theta, right? No theta. So we can use Fubini theorem here. This is integral from 0 to 2 pi d theta, integral from 0 to 3 of 18r minus 2r cubed dr. Okay, why do you do it that way, Thomas? Well, because I want to benefit from the fact that we integrate with respect to theta, but there's no theta inside the integrand, so it will be just the length of the interval here. Okay, times 18 divided by 2, that's 9r squared minus 2/4 r to the 4th from 0 to 3. That's 2 pi times 9 times 3 squared minus 1/2 times 81. 3 to the fourth, right? 3 to the fourth. But that's basically 81 over 2, huh? So 2 pi times 81 over 2, that's 81 pi. Okay, so the volume of this solid here, whose base is a circle, but you have a dome. You have a dome. Okay, the volume of this solid, is 81 pi. Let's go on with number 22. I basically do all even numbers, huh? Is it what am I doing? I think so. Wow, okay. Let me see, do I have more? Yeah, a couple more questions. So, but I want you guys to get used to this. It may be a new thing for a lot of you because I noticed some students coming to Calculus 3, they don't really know how to do polar coordinate systems, okay, and therefore they have hard time to understand polar graph in 2 dimension. Now we go to 3 dimension. Now we go to 3 dimension, and but there's no other way but getting the practice and get used to it though. Okay, number 22, let me do it here. Number 22, inside the sphere and outside the cylinder. Inside x squared plus y squared plus c squared equals to 16, and then outside x squared plus y squared equals to 4. Okay. If I try to graph this, visualize this, then the inside in polar, inside will be r squared plus c squared equals to 16, and then the outside is r squared equals to 4. If I draw this in 2-dimensional RZ, that's the first one, it has radius 4, right? If this is r and this is c, but r squared equals to 4 give us r equals to 2. So now imagine if you revolve this with respect to the z-axis. Can you imagine? Inside the sphere, outside the cylinder. Can you imagine? It's like you have a ball, but you cut the middle part away. We are talking only about this part here, but you revolve that. Okay, inside the sphere, outside the cylinder. Okay, if we see from above, let's say this is the z-axis. Let's say this is the z-axis shooting to us, right? Then you will see the domain actually looks like a donut with radius 2 to radius 4. That's what the domain looks like. That's what the D looks like. Okay. So the volume, oh, you know what? It's symmetric with respect to xy plane, right? So the volume will be, I will just make it 2 times double integral over that domain D and the upper part will be the square root of 16 minus x squared minus y squared dA. Think of it this way. Think of it this way. So if we see from the side, imagine that graph actually, this part here is this part here, but you rotate that with respect to z-axis. That's what we get. Okay, can you imagine that? It's kind of hard to graph it, huh? Well, anyway, so that will be the integral. Okay, I double it because it's the top and the bottom part. I double it because top and the bottom part. Now then I will make it into polar. That's 2 times integral from 0 to 2 pi, and then integral from 2 to 4 for the radius, square root of 16 minus r squared r dr d theta. Again, because it's independent of theta inside the integrand, okay, that will be 2 times 2 pi integral from 2 to 4. We're supposed to do the integral inside out, right? But because the outside integration theta is independent from whatever inside, then it will be just the length of the interval. That's square root of 16 minus r squared r dr. Now I will do substitution. U equals to 16 minus r squared. So du equals to negative 2r dr. U at 2 is 12. U at 4 is 0. So the integral now becomes 4 pi integral from 12 to 0 u to the power of 1/2 du over negative 2. This guy here, r dr, becomes du over negative 2. Okay, and 4 pi divided by 2 is 2 pi. I absorb the negative by reversing the order of integration, the limits of integration. Now I'm almost done. That's 2 over 3 u to the power of 3/2 from 0 to 12. That's 4 pi over 3, 12 square root of 12. I believe I can make it much better. For that 16 pi square root of 12, which is 2 square root of 3, then that's 32 pi square root of 3. Okay. Yeah. Do not rush to the integral. Okay. I think that's one of the big advice that I can give you. Do not rush to the integral. Set it up properly first. Please, please, please. Okay. And then when you do your integration, don't skip too many steps. I know you're in Calc 3, you can skip some steps, but don't skip big steps. Okay. What you don't want to happen is like you make a mistake, and then when you try to trace back your mistake, you kind of like spend more time you end up spending more time just to find your mistakes in the first place. You know, that's very unreasonable, basically. Okay, let me do a couple more. I think I will do one more from here and then another one from here. Number 26. I randomly pick numbers, by the way. I tend to pick even numbers because you don't have the solutions, so that you don't know if I did it wrong. Okay, actually you can find the solutions on internet though, but I think it's what I want to share with you, want you to learn is not about the answer, it's about how to set it up, and then to integrate that is something you expectedly already learned from Calculus 2. Okay, so our focus is more about setting it up. Okay, solid bounded by the parabolowitz. So this is z equals to 3x squared plus 3y squared. By the way, that will be 3r squared. And c equals to 4 minus x squared minus y squared, which is 4 minus r squared. If we try to imagine this, the first one is c equals to 3r squared. This is the r, this is the c, this is c equals to 3r squared. There's a open up parabola. Okay, and the second one is upside down parabola, 4 minus r squared. Too big. 4c equals to 4 minus r squared. Okay, now then we need to see where they intersect, right? Okay, so intersection, curve 1 intersect curve 2 will give us 3r squared equals to 4 minus r squared. We get 4r squared equals to 4, so r equals to plus minus 1. Because r is radius, we just take the 1. And then you rotate this with respect to z-axis, then you see it's basically you have the upper parabola and lower parabola intersect. Yeah, upper parabola, lower parabola intersect. The intersection will form a circle. As you can see here, the intersection is actually radius 1. Okay, it's a disk with radius 1. That's the domain. Okay, the upper part is the upside down parabola. The lower part is the paraboloid. Okay, so the volume equals to double integral over d of the upper part, that's 4 minus r squared, minus the lower part 3r squared dA. If we convert this then to polar, that will give us integral from 0 to 2 pi, integral from 0 to 1, right? That's why we find the domain, right? This is the domain. And then we have 4 minus 4r squared r dr d theta. Again, the integrand and inner integral has no theta, so integral from 0 to 2 pi d theta will give us just the length of the interval, right? In fact, I believe I can factor the 4, right? I can factor 4, so 0 to 1, r minus r cubed dr. So that will be 8 pi times integral from 0 to 1 of a polynomial, that's just the coefficient. So that would be 1/2 minus 1/4. That's 1/4. So 8 pi times 1/4, that's 2 pi. Okay. GS, do you have any question so far? Let me do one more question. Okay, the last one here. Evaluate the iterated integral by converting to polar coordinates. We usually do this anyway. If the domain looks ugly, follow the shape of the like if it's, you will see that if it is actually part of the disk, then it may be easier for us to compute that in polar. Okay, but let's take a look. The domain, the y is from 0 to a. The y is from 0 to a. The x is from negative pi of negative square root of a squared minus y squared to 0. Oh, the x is negative, So x equals to negative square root of a squared minus y squared, which means the x is negative or at most 0. When I square both sides and add y squared, okay, that's actually part of the circle. That's part of the circle with radius a centered at origin. Oh, hold on. The y is from 0 to a. The y is from 0 to a. So it's just the y is from 0 to a, and the x is from negative up to 0. So only this part here, huh? Only that part. Oh, then it's easy then. So the integral, now that integral from 0 to a, integral from negative square root of a squared minus y squared to 0 of x squared y dx dy now becomes integral from pi over 2 to pi, right? That's quadrant 2. Okay, and then the radius is from 0 to a. Okay, and then x squared is r squared cosine squared theta. The y is r sine theta times r dr d theta. Okay, clean it up a little bit. This is number 30, by the way. That's integral. Oh, the domain is a rectangle and the integrand is separable. Okay, so I will use Fubini's theorem here. That is cosine squared. Integral from pi over 2 to pi of cosine squared theta sine theta d theta times integral from 0 to a of r to the 4th d theta. Okay, this part here will be 1/5 a to the 5th, but the first part, I don't know. This is integral. If I use u equals to cosine theta, du will be negative sine theta d theta. Okay, cosine pi over 2 is 0. And cosine pi is negative 1. This is u squared, and this is negative du. Okay, that's integral from negative 1 to 0 of u squared du times a to the 5th over 5. So that is 1/3 u cubed from negative 1 to 0 times 1/5 a to the 5th. That's just 1/3, huh? This is just 1/3, right? Negative of negative 1 times 1/3 times 1/5 a to the 5th. That's a to the 5th over 15. Okay, that's for this section here, 15.4. Right now,